Ya, ahora sí, entonces agradecemos nuevamente a Irene por su presentación y damos la bienvenida al doctor Martin Yan Hei Li, doctor en Geología Económica y Química del Departamento de Ciencias de la Tierra de la Universidad de Hong Kong e investigador en Geoquímica para la Universidad de Brighton, Inglaterra. La investigación del doctor Li se centra en cómo ocurre la mineralización y la formación de yacimientos de tierras raras y todos los procesos sociales. Así que, muchas gracias, Martin.
Thank you, Paulina. Thank you for introducing me. Buenos dias. Good morning, everyone. I wish I could speak more Spanish, but pardon me, I have to speak in English for my presentation. But I'm Martin, and I'm from the University of Brighton, as Nicolás has introduced me. And today I'm very happy to be here to share with you some of my experience of working on this regularly post-rare deposit. And yeah, I think all of you know that the rare elements are this group of elements in the periodic table, and they are very important, right? Because they are the ingredients to make the permanent magnets, especially for wind turbine, when we are talking about renewable energy or zero carbon society, etc. And also they are used to make the battery for electric vehicle, also for the transition to a zero carbon society. So that's why rare elements, they are very important. And they're essential to a transition to a green economy, especially nowadays, we are talking about zero carbon. And that's why we are all here talking about rare earth today. But actually, we've got a lot of rare elements in the earth. They are well spread in the crust. The thing is that most of the reserves are in China. They're holding most of the resources that we have found nowadays. And more importantly, China is still controlling the production of rare elements nowadays. So when we know that rare elements, they're important, we need more of them to support the transition to a zero carbon society. But at the same time, China is controlling the production and the resources. So other countries, the United States, the UK, Canada, Australia, EU, and also here in South America, we want to look for our resources. And rare elements, as Irene has mentioned, we can classify them into light and heavy rare elements. For the light rare elements, they are mainly mined from the carbonatite and the associated alkaline intrusion. Like this one, the Bangor deposit in North China, the world's largest rare deposit. And for the heavy rare elements, they are mainly mined from the regularly post-rare deposit. That's why these deposits are important, and that's why we are talking about them today. And that's why I'm studying them for like quite a few years. For these regularly post-rare deposits, they are actually stored in the regolith, in the red product, in loose materials. And before I talk more about the geology and the formation of these deposits, actually nowadays, not only in China, we find quite a number of regularly deposits around the world, like in Africa, Madagascar, Malawi, Southeast Asia, in Vietnam, Thailand, Myanmar, and also here in Chile and Brazil. And here are some general characteristics of this kind of deposit. Compared to the carbonatite, the regularly coated deposit of the grade is much lower. Usually, we are talking about like 1,000 ppm or like 5,000 ppm, something like that. Compared to carbonatite, we are talking about 8% of rare element in those rocks. But the reserve and resources could be huge, could be up to like 10 to 100 million tons of rare oxide. And in these deposits, the rare elements, they are hosted in the regolith profile. And usually they are very thick. That's why most of these deposits, they are found in the tropical and subtropical region, where we have very intense chemical weathering to form the thick regolith profiles. And the rare elements are staying inside. And there could be different kinds of parent rock for the regularly hold rare deposit. Most of them are from granite. And also we have example developed from cyanide, calcium volcanic rock, and even metapelite, the metamorphic rock, metamorphic sandstone. And even though we are talking about heavy rare elements, whenever we mention the regularly hold rare deposit, actually we can still divide the regularly hold deposit into heavy rare rich and light rare rich. In general, compared to the carbonatite, these regularly hold rare deposits, they have much higher concentration of the heavy rare elements than the carbonatite.
Hola, ¿se escucha? So we'll find again.
Okay, yeah, perfect. Yeah. Thank you. Yeah, we just stopped when we're talking about why we are still mining this deposit, even though the grade is so low. It's because the mining method can be achieved in very low cost. In China, we use this kind of in situ leaching to inject the ammonium sulfate solution from these pipelines into the regolith. And when the ammonium sulfate solution flows along the slope in the regolith, they leach the rare elements out from the regolith, and eventually people just make this kind of pond at the slope toe to collect all the solution to further extract the rare elements out. This kind of mining method is very, very low cost. That's why even though the grade is low, the mining practice is still achievable. Is okay?
Yes.
And this deposit, they are hosted in very thick regolith profile, and usually this problem. Yes, yeah, thank you. Okay. And usually this regolith host deposit, they are hosted in the regolith profile, and for a complete weathering profile, regolith profile, from the bedrock, the fresh rock, all the way to the most weathered material on the top. Here is the complete profile, and I would like to introduce to you some terminology before we go on, because I'm going to mention that a few times in the presentation. Like we have the fresh bedrock, usually they are granite at the bottom, and after weathering, joints developed, and we have iron oxide, clay mineral, especially along joints, decomposition of feldspar and mica to form the sap rock, but they're still very hard, very strong. With more and more weathering, we got a layer of saprolite overlying the sub rock. Now we have the loose material. We can break it easily with our bare hand. But still, you can see from this photo, the granite, the original texture of the granite can still be preserved in the saprolite layer. But eventually, with very intense chemical weathering at the top of the regolith profile, everything are destroyed and replaced by plain mineral, iron oxide like goldite, hematite, etc. to give the brown color. And we have now the top petalite layer. Basically, it is soil on the top of this profile. So this is a very typical regolith profile we see in this deposit, hosting the rare elements. And just let's look into some example of the regolith host deposit around the world, like the Serra Verdes deposit in Brazil. It is a light rare rich deposit formed under tropical climate with high temperature, high rainfall, more than 1,500 millimeters per year. And this is the result, about 900 million tons at 0.12% weight percent of rare oxide. And it is developed from alluvium and rare rich granite with regolith profile of 20 to 40 meters thick. And you can see very well developed layer of saprolite and also the petalite layer on top of it. And other regolith host deposit that is well studied and well explored would be this one in Madagascar. And again, this is a light rare rich deposit developed under a tropical climate with high temperature, high rainfall. You can see that's why we are finding this deposit usually in the tropical and subtropical environment. And also this is one thing that the deposit here in Chile are very special because we are out of the subtropical zone. We are kind of in a temperate climate. So the story could be different. But anyway, most deposits up to now we know are in the tropical and subtropical zone. And I think this one is light rare rich, but the potential for this deposit is very variable. We have regularly developed on cyanide too, and also some type of pegmatite. And the rare concentration in the regolith is the highest for those developed on the cyanides. And that could also partially due to the original rare concentration of the parent rock, because we find that the rare concentration in the cyanide is the highest among all these rock units. So probably that's the reason why we have the highest concentration of the rare elements in the regolith from the cyanides. But today, I would like to draw your attention to the Chinese deposit, because I've been working on this deposit for many years, so I have a lot to tell you. And I will illustrate to you the ore forming mechanism, ore forming processes, and the factor behind controlling the formation of this deposit in China. Two examples. The first one is called the Judong deposit, and the second one is called the Bankan deposit. And one is heavy rare and which the Judong deposit, and the other one is light rare and which the Bankan deposit. So we can compare between the two to see what is the reason behind to control the formation of a heavy rare regolith deposit or a light rare rich regolith rare deposit. So both deposits are developed on granite, but the granite are different. The Judong deposit, the heavy rare rich one, developed from muscovite-bearing alkaline granite, and originally the granite is quite rare rich. You can see the concentration can be up to 7,000 ppm. And for the light rare one, it is developed on a biotite granite, and this one is like average rare concentration of a normal granite, 200 to 400 ppm. And both deposits, they are in South China, developed under a tropical climate of like this range of temperature and rainfall. And when we talk about the mineral deposit, the first thing will be the source. Apparently, the potolith would be the source of the rare elements, right? because regolith developed from weathering of rock, but it is the case. So now we study the bulk geochemistry of the regolith and the bedrock, and we find that actually the regolith inherits the rare pattern of the bedrock. Like here from the Judum deposit, this is the normalized wear pattern of the bedrock. It is already heavy wear and rich for the bedrock for this Judum deposit. And for the other, the light wear rich can deposit, you can see the bedrock wear pattern. This one is light wear rich. And for the regolith developed on it, they followed similar wear patterns to the bedrock, except cerium. So cerium behave differently to the other rare elements during weathering, but nevertheless, overall speaking, if we want a heavy rare deposit, the first thing we would like to do is to find a heavy rare rich bedrock, to look in the literature to find something having this kind of pattern. So it will be a good sign for us to find a heavy rare deposit. And the minerals inside the rock to host the rare elements are very different too. For the Judum deposit, the heavy rare deposit in the bedrock, there are different kinds of heavy rare minerals, including the synthesite, which is a fluorocarbonate mineral, some rare silicate minerals, including this one, gadolinite and hicknite, and also some more common rare minerals like xenotite. This one, yeah. But for the light rare element deposit, the rare minerals inside the bedrock are different, and they are light rare rich too, including apatite, monazite, and also some of the fluorocarbonate mineral. They are the common rare minerals in the granite, allanite, and titanite. In summary, there are many different kinds of rare minerals that we can see in the rock, in the granite. They hold the rare elements. But the point is that if these minerals are not going to be rare during weathering, the rare elements they are hosting are not going to be released to the regolith to form the deposit. So which mineral they are the good minerals and which mineral they are not the good minerals for the rare elements to be released during weathering? Actually, there are some kind of experimental work in the literature, but not really that much on all these different kind of special rare minerals. So what I did is a very basic thermodynamic calculation, trying to predict which minerals they would dissolve during weathering and which won't. And what I find is that this mineral in the red square, theoretically, they should dissolve very easily during weathering. And look at this mineral. Actually, I've just mentioned them in for the heavy rare rich granite. They host most of the rare elements in that granite. And allanite are very common light rare mineral that we find in the granite where we have the regolith deposit developed. So these are the good minerals. But for these minerals in the blue square rectangle, they are not really that good property, because like here the calculation indicates that they are not easily dissolvable during weathering to release the rare elements. And also here are some other kind of common rare minerals in the bedrock we observe from other deposits, like the eudialyte, grapholite, and also the fergasonite. Some of these minerals, they could easily dissolve during weathering, and actually we find quite a lot of this mineral in the bedrock of regolith deposit around the world. So they're good, and some of them they are not that good. So that when we look into the mineralogy of the rock, if most of the rare elements are hosted in these minerals that could be easily dissolved during weathering, there will be a good signal, right? Because during weathering, this mineral could be easily dissolved to release the rare elements for them to be accumulated in the regolith to form the mineral deposit. And some of them, however, if most of the rare elements are hosted in these minerals. Probably they are quite strong, and they're strong enough to host the rare elements, withstand weathering, so that would not be a very good sign for the development of regolith host deposits. And the next question is that we got all these minerals, some of them now we think they are the good mineral, and if most of the rare elements are hosted in this mineral, that will be good for the rock to release the rare elements to weathering to form the regolith host deposit. But what would be the reason for this mineral to form? And that could be due to hydrothermal alteration, very intense hydrothermal alteration. When we look into the bedrock, this granite, we find that in most cases, the circle, they are porous, and unlike the normal circle we expect from a granite that is transparent under optical light and homogeneous under the electronic microscopic imaging, they are very porous and beta corroded. So there must be very intense hydrothermal interaction between the granite and the hydrothermal fluid to form these rare minerals, to upgrade to form these rare minerals. So what I've done, I've analyzed the chemistry of the circle, trying to trace the hydrothermal alterations to see the dynamic of the rare elements during this interaction. And actually, what I find is that, like here, if you look at the variation of the rare elements in the circle, they show variation and fluctuation, and which indicates a multiple stage of hydrothermal alteration of the rock to form these rare minerals. So in other words, hydrothermal alteration, they will be very important because they prepare the rock, they enrich the rock with rare elements. And remember that some rare minerals, they could be very strong, like monazite, zircon, singletite, and probably even the apatite or titanite. They could be very strong and they could withstand the weathering to release the rare elements they host. However, alteration can weaken the structure of this mineral, and some people, they observe the formation of different kinds of nanoparticles during the hydrothermal alteration that could weaken the structure of this rare mineral. That may facilitate the dissolution of this mineral to weathering to release the rare elements to form the regolith host deposit. So here we see hydrothermal alteration is very important. Not only granite itself could form the regolith host deposit, but the granite will need to be intensely hydrothermal altered to enrich the granite in different kinds of easily weathering rare mineral, and at the same time to enrich the granite in rare elements. So a brief summary about the source, the nature of the bedrock from the regolith host deposit. First of all, if the rare concentration of the rock is higher, definitely that will be higher, right? Or rare elements ready to be released to a weathering to form this deposit. At the same time, we see that the regolith inherits the rare pattern of the bedrock. So if we're looking for a heavy rare deposit, what we want to find is a heavy rare rich rock. And finally, hydrothermal alteration is very important. It could enrich the granite in rare elements, and also at the same time, it can alter the mineralogy to form those easily weatherable rare minerals, so that rare elements can be steadily weathered. And now we got the rare element out of the rock with weathering, and they will be mobilized. What would be the medium to mobilize the rare elements with weathering? There will be water, right? Rainwater, groundwater. And in South China, we see that in most cases, the groundwater is neutral to slightly alkaline pH. At the same time, they are carbonate rich. And trying to figure out the rare earth speciations in the groundwater, I calculated like based on thermodynamics, and the results show that most of the rare elements they are transported as carbonate cation, especially for the heavy rare elements. While the light rare elements, more of them are transported as free cation. And that will be something important to the mobilization of the rare elements in the weathering. First of all, we have the vertical mobilization. We have the infiltration of the rainwater, groundwater from the top all the way to the bottom of the regolith profile. So very often we see a gradual increase of the rare earth concentration from the top to the interface between the petalite and the saprolites, where we usually find the ore body. So we have the vertical mobilization, the leaching of the rare elements from the top to this part, then they start to accumulate. But what we see is that usually the light rare element, they start to accumulate first. When we compare the geochemical composition of the regolith from different parts of the regolith profile, we see that the light rare elements are more preferentially enriched in the ore body. So in other words, all rare elements, they are leached from the top downward, but the light rare element, they got accumulate first. They will be due to the speciation. Remember that the light rare elements, they are more preferentially mobilized as weak iron, while the heavy rare elements, they are mobilized mainly as carbonate complex, which is very, very strong. And so that the heavy rare elements, they tend to stay in the groundwater. Just before we go to the talk about the heavy rare elements, regarding the depth of the ore body, in some cases, when the petalite is not granite, if the petalite is alkaline rock or metapelite, usually we find the ore body is located at a shallower depth. And that probably is due to the nature of the regolith. In alkaline rock, in metapelite, there is a lack of pores. So the porosity and the permeability of the regolith may be lower, so that the leaching may not be that efficient, and the accumulation of the rare elements would occur at a relatively shallower depth. And coming back to the transport and mobilization of the rare elements, now we've got the vertical mobilization, but in this sense, the light rare elements is trapped first, and they will be enriched first. While the heavy rare elements, they tend to stay in the groundwater and be mobilized laterally downslope. So that in some cases in South China, we see light rare elements, they are more enriched at the top of the hill, while the heavy rare elements, they exist as carbonate complex in groundwater and being transported by the groundwater all the way to the slope toe, where we see more enrichment of the heavy rare element than the slope at the toe. And that would have some implication for the exploration. First of all, we see vertical mobilization of the rare elements, so that usually the ore body is located at the interface between the petalite and the saprolite. That's where we want to do, from the field, we can identify this interface, right? So that would be the first thing we may want to investigate, to study, to analyze the geochemical composition, to see whether we have the rare mineralization. And secondly, we have rare fractionation during the transport of rare elements in the surface environment, Earth's surface environment. And we find light rare enrichment at the top of the hill, while heavy rare enrichment at the slope toe. So if we are doing exploration, that could be some kind of geomorphological factor that we could consider to locate our target. And finally, we need something to track the rare earth elements in the regolith, so that eventually we have the ore formation, right? And from the nature, you know that this kind of deposit, they could be leached very easily. We can use ammonium sulfate solution to leach the rare earth out. So definitely the rare earth element, they are loosely bound to the regolith. It's because most of the rare earth elements, they are hosted through absorption on the clay minerals. Like this one, the Judong heavy rare earth deposit, we find that about 60% of the rare earth elements in the ore body are sorted on the clay minerals. And a little bit of the rare earth element is hosted by the iron and manganese oxide, and the rest are stored in different kinds of residual and supergene rare earth minerals. And at the same time, the bonding between the rare earth elements and the clay mineral must be weak, so that we can leach them out very easily. And some other research with synchrotron, like kind of a beamline technique, using a very fast moving beam to hit your sample, so you can do very high resolution analysis on the clay surface. And what it finds is that, yes, the rare earth elements, they are loosely attached to the clay surface through electrostatic force, or we can call it outer sphere compensation, or in other words, very loose complex on the clay surface, so that we can leach them with ammonium sulfate solution easily and recover the rare earth elements. And now we know the clay, they are important because they absorb the rare earth elements. But we also know that like clay, they don't stay steady in the regolith. They change with weathering. When we have the regolith profile, and a different part of the profile, the degree of weathering is different too. And how would the clay mineral in regolith host deposits change with weathering? First of all, we need to find out what kind of clay mineral we can see, what kind of mineral exists in the regolith. Actually, what we find is that through the entire profile, kaolinite and halloysite are two major clay minerals in the regolith. But they look very different. They look very differently when we find them in the lower part of the regolith profile, where the kaolinite is irregular in shape and very small. Also, the halloysite, they are very small, like a few micrometer in length, and also the shape is not well developed. However, when we move to the top of the regolith profile, to the more weathered material, we see the kaolinite and halloysite are much more good looking, much more larger, much more crystalline, much more euhedral. Like here, you see the kaolinite is showing you the typical black appearance, while the halloysite is showing you the tube appearance, the good looking, the typical tube appearance. So even though we are finding similar clay mineralogy or similar type of clay mineral through the entire regolith profile, but their appearance are totally different. And also the physical and chemical properties of the kaolinite and halloysite from the lower part of the profile are very different to those at the upper part of the profile. And before I go to the physical and chemical properties, we also see the recrystallization and transformation from the irregular shape, the poorly crystallized kaolinite and halloysite, to the well-developed, well-crystallized kaolinite and halloysite at the top of the regolith profile. Like here, I would like to show you an example. This is a kaolinite booklet under development. And if you zoom in, you can see actually it is formed by this nano tube of halloysite sticking to the edges of the kaolinite booklet and starts to recrystallize and transform to the sheets of kaolinite. Similar thing happens at the basal surface of the kaolinite. Again, if you zoom in this part, you will see this halloysite tube sticking to the surface of the kaolinite and unrolled to form a layer of kaolinite, so that with more weathering, the poorly crystalline kaolinite and halloysite gradually recrystallize to the well-crystalline euhedral kaolinite and halloysite. And during this process, the physical and chemical properties significantly change. For example, the surface area of the clay mineral greatly decreases. And also the pore volume, the porosity of the clay mineral also greatly decreases when we move from the lower part of the regolith profile to the top of the regolith profile. And at the same time, we see the recrystallization of the clay mineral, the crystallinity increases. And altogether, all these parameters contribute to the ability of absorption of the clay minerals. And now, when the surface area decreases, the pore volume decreases, and the crystallinity increases, the absorption capacity of the clay mineral in the petalite, in the shallow part of the regolith profile, greatly decreases. That could cause the desorption of the rare element in the petalite, while the rare element will be mobilized vertically downward to the interface between the petalite and saprolite, where the poorly crystalline kaolinite and halloysite would have a great absorption capacity to absorb the rare elements again. And that is exactly what we see when we analyze the clay mineral we separate from the regolith. Apart from the clay mineral, we also have the iron oxide. However, the iron oxide, from current understanding, they are not really important in terms of hosting the rare elements in the regolith post-deposit, except cerium. Like here, when you look at this part of the graph, you can see nearly all of the cerium are hosted by the iron oxide at this Bankan deposit. And also from the EDS mapping, we can see that the cerium is strongly associated with the iron oxide. So in other words, the iron oxide, they may not be very important in hosting the rare elements in the regolith post-deposit, but they could host a lot of cerium, even though our cerium is not the main target that we are targeting for from this deposit. And finally, we also have different kinds of ragged mineral. They are the residual mineral survived from weathering, like zircon, monazite, or xenotime. As I mentioned, they are very hard, so they can survive from weathering and exist as ragged minerals in the regolith. And also, there are some kind of supergene mineral, which means they form during weathering. This mineral, they could host a proportion of rare elements, up to 20 to 30% of rare elements in the regolith. But however, at this moment, we don't have a method to extract the rare elements from this mineral. So some of the key message about clay mineral and the sink of rare element in regolith. The clay mineral, especially halloysite and kaolinite, they are very important. They are the major hosts of rare elements in regolith post-deposit. And their property significantly changes associated with weathering. And we see that in the highly weathered petalite, the absorption capacity of the clay mineral actually are quite low, so that where absorption happens in the shallow regolith. And in turn, the rare element will be mobilized vertically downward to the ore body, to where we find the ore body, where we have the poorly crystalline kaolinite halloysite, providing a high capacity of absorption to absorb the rare elements. And finally, iron oxide, even though they are very abundant in the regolith, they are not a major rare element host, except cerium. And finally, with forming model, if we want a heavy rare element deposit, first of all, we want to find a heavy rare rich granite. And these are some minerals that could easily dissolve during weathering. So if we just pick up granite and if we analyze it, if we impose a lot of rare element and this kind of minerals, there will be a good sign for the development of heavy rare deposit. And also at the same time, we have the formation of halloysite during early stage of weathering to host the rare elements. And with time, with more and more weathering, you see the clay mineral, they will be crystallized, but associated with the recrystallizations, the absorption capacity decreases. So rare earth is dissolved in the shallow part of the regolith profile and being transported downwards to the deeper part of the regolith profile where the clay minerals are still poorly crystallized and have a strong ability to absorb the rare elements, so that the rare elements are gradually accumulate to form the ore body. At the same time, we have the lateral transport, especially for the heavy rare element. They want to stay in the groundwater, so they could be transported quite a long distance, or like in the cases, in the South Chinese case, we see them being transported all the way from the top of the hill to the plateau. And eventually, rare elements accumulate to form the economic regolith deposit. And finally, before I finish, I just want to introduce something I've started working recently about the exploration, some techniques for the exploration of rare elements. And from previous study, we find that neodymium, this rare element, can give short-wave infrared reflectance. And with some kind of software processing, we can magnify the reflectance so that we can estimate the neodymium concentration in the regolith by the magnitude of these peaks. At this stage, what we are doing is laboratory-based analysis. This is the equipment we use in the lab. But I see, and I'm hoping that eventually we could develop to use the handheld portable equipment or some kind of field-based equipment for studying the regolith on-site with the IR techniques, like for very good exploration techniques. And here are some preliminary data we got from analyzing the South China samples. And we see that the signal, the IR signal of the neodymium match quite well with the chemical composition we determined from SPMS. However, in some cases, in some deposits, the result is not really that good, and that could be due to the iron content in the regolith. So this is some kind of preliminary data, and I'm showing here just like want to stimulate more discussion and on this topic. But you may say we can also use portable SRF to determine the shear concentration of the regolith on site. But as you know, not all the rare elements are hosted on the clay mineral. Not all of them are easily extractable, but that is just the portion we want. But with the IR, apart from the neodymium concentration, we can also analyze or we can also estimate the abundance of the clay minerals. Like here, we try to compare some kind of parameter we extract from the IR reflectance with the abundance of kaolinite mineral we determine from SRD. And the result is quite promising. We see some kind of correlation in some cases. And also, apparently, some parameter from the IR reflectance could indicate the crystallinity of the clay minerals. As I just mentioned, the crystallinity of the clay mineral will be very important in affecting the capacity and absorption capacity of clay minerals. So hopefully that could be utilized as an indirect indicator for the abundance of kaolinite, halloysite, and even the vicinity of the clay minerals. And that's also something we are doing at this moment, hoping in one day we can develop it as an exploration tool. And finally, thank you very much. Oh, yeah. I always welcome to drop me an email and or a message in LinkedIn or research PAs. Yeah, it will be great to have more discussion with all of you. Thank you.
Thank you, Martin. Tenemos tiempo para algunas preguntas. Si quieren alguna pregunta para Martin.
I would like to know if I understand something well about the presentation, that the position of the ore body into the regolith with what variables is associated, like if it's the crystallization of some minerals, the porosities that move the ore body over or not into the regolith.
Yeah, a very good question. Actually, there are many factors affecting the position of the ore body. But in general, we see the ore body located at the interface between the petalite and the sublet. And why? Because it is actually a weathering front. Usually we see a significant increase of the pH of the regolith across this interface. And what I didn't mention in the presentation is that the absorption of the rare elements or the clay minerals is highly affected by the pH of the system. When the pH is higher, absorption usually is stronger. So when we are talking about weathering front, where we have a certain increase of pH, it will largely facilitate the absorption of the rare elements from the clay minerals. That would be, I would say that would be the primary factor controlling the ore body, the location of the ore body. However, there are more than that, like the porosity of the regolith, like for the regolith developed from alkaline rock and metamorphic rock, usually there is a low amount of pores in the regolith, or the regolith is more fine-grained, so the porosity and permeability are lower, and the infiltration is less efficient. So probably in this case, the ore body will be located at a much more shallow depth. And the other factor would be due to erosion, right? If erosion happens, removing the top part of the regolith profile, the ore body will be exposed. Yeah. So that would be other secondary factors affecting the position of the ore body located. Thank you.
Thank you very much.
Yeah, thank you.
¿Una pregunta por ahí?
Puede ser en español.
Sí, también puede ser en español.
Yeah, I understand this.
I have a question.
Yeah.
You said to me prior to your presentation that you were researching patio weather regoliths. So, or something. Yeah, right?
Yeah.
Yeah. So have you found some evidence on enrichment on patio regoliths? Or something that you can discuss with us about it?
I think at this moment, I can't draw a conclusion on that. Yeah. And I think for the paleo system, that would be much more complicated. Definitely, I think the modern weathering would also happen in the past in a similar fashion, so that rare element also got mobilized and somehow enriched at a certain position of the regolith profile. But after the formation of the regolith profile, there could be burial of the material of it that further provide the rare elements to the system, or that could be the deformation of the ore body, so that rare element is lost. And at this moment, I think from what I know, we don't have conclusion on that yet. Yeah. Or like what kind of situation would be favorable for a paleo system to be served. Yeah. But yeah, there's a good direction for further research. Yeah.
Thank you.
Pasa que en el depósito de pulpo, donde vamos a ir, la mayor parte del regolito que está enriquecido, la roca caja es un granito que contiene mucho granate. Y el granate tiene en sus concentraciones tierras raras pesadas. Entonces quiero saber si existe alguna relación, o si se sabe anteriormente, si es que estos granates también tienen una influencia en el hecho de que el enriquecimiento en el regolito sea mayor en tierras raras pesadas. ¿Qué es lo que pasa entre?
So, she was talking about the deposit in Penco.
Sorry?
This deposit in Penco in Southern Chile. No, Chile, Concepción.
Okay.
Yeah. And as I told you, this deposit is the parental rock is a garnet donalite, garnet granite. So she was asking if and she said that a lot of the garnet has lots of heavy rare earths.
Yeah.
But it doesn't get so easily weathered.
Yeah.
So she was asking if you could if you could explain us what could be the role of such a mineral like garnet on the enrichment of heavy rare earths on those regoliths because of the weathering or something like that.
First of all, I have one question after listening to your question. Is the granite being altered hydrothermally? Is there any
Altered?
Yeah, is there any hydrothermal alteration?
There is, yeah.
Yeah, if there is no hydrothermal alteration, I would expect the garnet is very euhedral, very strong, and in that case, they would be very strong to weathering, and I would expect kind of residual report rather than I am something of big minerals. So the garnet may stay there and got accumulated when the other minerals decompose and have the heavy rare ambition in this case.
Just a small fraction of the garnet gets wet.
Yeah. But if I'm not sure like how much did the hydrothermal alteration affect the garnet? Are the garnets good looking, euhedral? No. Yeah, so if not, probably the hydrothermal alteration may play a role in weakening the structure of garnet. Like I've shown you in the presentation in South China, we see many strong minerals like monazite, sinotite, zircon. They are highly ordered. If they are not ordered, I won't expect them to be rare, to release the rare elements. But after hydrothermal alteration, their structure deteriorated. So they got the chance. Yeah, exactly. So probably that would be one way for the rare elements to be released to the garnet, or the other way if the garnet is very euhedral, very ordinary. So the rare accumulation could be achieved through the residual accumulation of garnet in the regolith.
Thank you.
Thank you so much. Yeah.
Thank you, Martin, for your presentation. I was thinking about exploration techniques, and do you think that, for example, surface water chemistry can be useful to exploration of this kind of deposit? Or, for example, sediment chemistry?
Yeah. Very good question. Yeah. For water chemistry, I think yes. First of all, you can analyze the rare concentration in the water, and also other anion, so that you can do very simple thermodynamic calculation to see how rare elements are transported in the water. If they are, if the water, also you can determine the pH of the water. If the pH is very low, usually it won't take absorption on the clay mineral. What we are seeing is usually slightly acidic to neutral to slightly alkaline groundwater in South China in these deposits. Yeah. So and also from the speciation of the rare elements in the groundwater, you can predict whether they could be easily absorbable on the clay minerals. In that, actually, there are quite a lot of experimental work, pure experimental work being done on the compensation between rare elements and pigments and iron in water, and to see how that would affect the absorption from the clay minerals. And that could be some kind of reference to indicate or like to evaluate whether there would be a lot of absorption on your sample. So I think that would be valuable to have the water chemistry for the exploration.
Okay, thank you.
Hi, Martin. Thank you for your nice presentation. What do you two questions? In China, you have identified another clay mineral like alite or other one that in the change of the pH probably is generated. Oh, this is one question. And the other one, what do you think about in the case of the fractionation and mobilization of the rare earth? Is possible to generate just regularly the rare earth deposit just with the alteration minerals, yeah, not with the bedrock granite rich do you understand?
Yeah. I think I get it. Yeah. For the first question, you're asking about like, are there other clay minerals like elite, the smectite, etc.? Yeah, they exist in the regolith, but in a quite a low abundance compared to the kaolin and colloidite, and usually they are not located in the whole body. They are either in the very deep part of the regolith profile or at the top of the regolith profile. Definitely, there could be some rare elements being absorbed on elite, smectite, and other clay minerals, and whether that would be very important would be something we need to further study. But at this point, we don't see them contribute significantly to the accumulation of rare elements in regolith. And for the second question, talking about the rare fractionation, I would say at this point, from like all the regolith host deposit finds in the world, and from all the data we have, we still see that there are very strong inheritance of the rare patterns in the regolith through the bedrock. So yeah, rare elements fractionate during weathering, as also I show in my PowerPoint slide, but the degree of fractionation is not great enough to really change the rare patterns. So we are still thinking that the bedrock, the nature of the bedrock is a first order control to the formation of either a light rare earth rich or a heavy rare earth rich regolith host deposits.
Yeah, I was thinking like the exotic deposit, the copper. It was.
Yeah, that could be possible. Yeah, if we find one, that would be very interesting to start. Yeah, definitely. Yeah, I think for laser deposit, or if there are some kind of sedimentary deposit being found recently in Australia, and it is said that the rare earth elements are being transported a long way, like a sedimentary process, so that the source is not the bedrock in the surrounding area, it's from very far away. And in that case, probably the recognition will be significant enough, to really change the wear patterns.
Thank you, Martin.
Thank you.
Thank you very much, Martin.